Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. Today's lecture is partially a continuation of the two-stage least square methodology or estimation technique. And after that, we will move to three-stage least square estimation. We'll see why do we use three-stage least square, when to choose between 2SLS and 3SLS, what is the advantage of 3SLS, or sometimes 2SLS is better. We'll be looking into these matters. And also we'll see how, for exactly identified equations, 2SLS and indirect least square provide the same result. We'll look at it theoretically, and then we'll have a numerical example for that. First, let's briefly look back into other estimation techniques like ordinary least square. In ordinary least square, you remember that we had a single equation where we had a dependent variable and the explanatory variables. In fact, the dependent variable is the endogenous variable in that equation, and the right-hand side variables are exogenous. If there are endogenous variables on the right-hand side, and we have more than one equation, we cannot use ordinary least square, we cannot produce consistent efficient estimates. So when we have simultaneous equation models, we switch to other types of estimation techniques. Based on the identification status of each equation, we try to estimate it by the relevant methodology or technique. For example, if the equation is exactly identified, we try to use indirect least squares. If the equation is over-identified, we have the choice of two-stage least square instrumental variable or three-stage least square methods. So in this way, when we look into the identification status of an equation, we have the ability to choose an appropriate technique to estimate the parameters, what we call structural parameters of the equations. So in OLS, we have one endogenous variable on the left-hand side, and we have exogenous variables on the right-hand side. So when we have system of equations, we have several endogenous variables, maybe on the left-hand side, or they may exist on the right-hand side. So if we have endogenous variables on the right-hand side of an equation, in a system of equations, we cannot use OLS because one dependent variable of, say, equation 1 may be related to the error term of equation 2. Because if you remember, when we had two equation system, we substituted the second equation into the first one. In that way, the first dependent variable becomes a function of the error term of the second equation. So in a system of equations, the structure can be that one endogenous variable may be related to the error terms of some other equations. If we use OLS, we wouldn't be getting appropriate estimates. So this is why we switch to techniques like indirect least square and two-stage least square. Now, when a variable is endogenous, it may be, as I told you, correlated with the error terms of the other equations in the system. We use two-stage least square in order to account for this kind of problems. When we use two-stage least square or indirect least square, we are dealing with a system of equations. We find the reduced form of the equations, and with the help of the reduced forms, we try to estimate the structural parameters of the model. For example, if we have structural parameters like alphas and betas and gammas in a system of equation, these structural parameters can be written as an expression of the reduced form coefficients. If you remember, the reduced form coefficients are labeled as pi with a subscript, and those pi's are estimated through OLS. So indirectly we use OLS. So we use OLS when we have the reduced form equations. Why do we do that? Because in the reduced form equations, if you remember, we have only exogenous variables on the right-hand side. We have, in fact, cleaned the endogenous regressors out of the equation, and now we can apply OLS to single equations, the reduced form equations, where the endogenous variables are written as a function of the exogenous variables only. So if you remember, we had the reduced form equations, we had endogenous variables on the left-hand side, and we have all the exogenous variables of the model in each equation, in each reduced form equation. Whether it existed in the original equation or no, we have all the exogenous variables of the model in one reduced form equation on the right-hand side. So we used OLS to estimate that. Now either we use the pi's or reduced form coefficients by the expression in which we have expressed alphas and betas, the structural parameters. We use that information, that estimations by OLS, to estimate the alphas and betas indirectly. This is called indirect least square. And sometimes when we have over-identified equations, we use two-stage least square. In that way, we have the estimations in two different stages. First, we try to, as I told you, have theoretical values of the endogenous variables. For example, if y2 is endogenous on the right hand side of equation 1, where you have y1 as a left hand side variable, first we estimate the theoretical values of y2. We do that with the reduced form equation of the endogenous variable y2. So we write the reduced form equations, we estimate y2 with the help of ordinary least square and find the trend values which we call y2 hat with the help of OLS again. We are using OLS here. So when we have those trend values, which I am calling now theoretical values, then we substitute or replace the original endogenous variable on the right hand side of the first or whatever equation we are considering, and then we, with the help of these theoretical values, we regress the endogenous variable on the theoretical values of the right hand side endogenous variable or variables if we have more than one. In this way we get the 2SLS estimates of the structural parameters of the over-identified equation. So the logic of using 2SLS is to find a proxy that is not related to the error term of the second or third or whatever equation you are considering. So if we have two equations, in fact we have an endogenous regressor on the right hand side of equation 1, suppose this is the case. Now that endogenous regressor is related to the error term of the second equation. So you want to clean that. We find a theoretical value, which is your y2 hat, as I told you, which is not related to the error term now. It's a theoretical value estimated by OLS. We use that value in order to regress the first endogenous variable on this theoretical value of the second endogenous variable. This process is called two-stage least square. So p hat or y hat or whatever you are computing with the help of OLS as a theoretical value should not be correlated to the error terms of the second equations or third equation or whatever system of equations you have. So this is the logic of using two-stage least square. We have used it in an example. So after performing the two-stage least square regression, there is a test that we need to perform to look into whether the regressors were really endogenous or no. This is a post-estimation command. So in Stata, we would be using it after the 2SLS regression. For example, after the IV regress. So when we use that, we come to know whether the regressors were really endogenous or no. Let's see how to perform that test. Remember that it's a post-estimation test. If you have already performed a two-stage least square estimation process, then you can apply this test. The test is called Durbin and Wu-Osman test, and it is, as I told you, used after the IV regress command which you have been using. The command is estat endogeneity, and the results are given below it. So this is a test of endogeneity where the null hypothesis is variables are exogenous. That means the variables are not endogenous. So the Durbin score chi-square is 5.47 with a p-value of 0.01. We can reject H0, and the Wu-Osman F value is 8.48 with a p-value of 0.02. So as both the p-values are less than 5%, we can reject H0 of exogenous regressors and conclude that the variables are in fact endogenous. So this was done with the example in the previous lecture where you were thinking that C and T variables were endogenous. So we applied a test basically, which you can see in the Excel file that is provided to you, 2sls.xls or 2sls2.xlsx. So these two files have some examples that you can use to perform the estat endogeneity command, and that will give you, if the values, the p values are less than 5%, then you may conclude at 5% level of significance that the regressors are endogenous. If the values are less than 1%, then you can conclude at 1% level of significance that the endogenous, that we have endogenous regressors, and it is justified to use 2SLS. So two-stage least square technique is a good technique which takes care of the fact that one endogenous variable is related to the error term of the other equations in the system. Now, as we have discussed indirect least square as well as two-stage least square, let's look into how two-stage least square and indirect least square may provide identical estimates for equations that are exactly identified. If you remember, we have used some Stata commands, for example, reg3 and IV regress, to apply two-stage least square. and we had no direct command for indirect least square, we could do that with the regress command. But as we know that for exactly identified equations, if we apply 2SLS to them, we will get the same results as if we had applied indirect least square. So let's do that theoretically first, taking a model, considering a model, and then we'll have some values which are provided to you in the Excel file, which will enable you to see really that ILS and 2SLS will provide identical estimates if the equation is exactly identified. I mean one of the equations in the system, one or more. At one time you are considering one equation, remember this thing. So in 2SLS also, we are focusing on one single equation, which is most probably over-identified. So let's see by taking an example of a model that is displayed on the screen in front of you, where we have two equations. Y1 is alpha naught plus alpha 1 y2 plus E1, which is the disturbance term of the equation 1. Y2 is beta naught plus beta 1 y1 plus beta 2 x1 plus E2, where E2 is the residual or disturbance term of the second equation. So clearly we have a system of equations where we have two endogenous variables, y and y2, located on the left hand side as well as on the right hand side in each equation. For example, y2 is on the right hand side of equation 1 and y1 on the right hand side of the equation 2. If we substitute one equation in the other and have some algebraic manipulation, we can find the reduced forms of both endogenous variables y1 and y2, which are also given to you on the screen. Y1 is pi 1 naught plus pi 1 1 x1 plus u1, where u1 is the disturbance term of this reduced form equation. And y2 is pi 2 naught plus pi 2 1 x1 plus u2, where u2 is the residual or disturbance term of the second reduced form equation. If you do this process on paper, you can easily see that the substitutions we made here are pi 1 1 is equal to alpha 1 beta 2 by 1 minus alpha 1 beta 1, and pi 2 1 is beta 2 by 1 minus alpha 1 beta 1. So now let me tell you about the process of ILS and 2SLS that we are going to apply here. In indirect least square, we only use these expressions because we are able to express the structural parameters alphas and betas in this model in terms of the reduced form coefficients. So we can easily use this expression to write alpha 1 or alpha naught in terms of these pi's or reduced form equations and estimate these reduced form equations through OLS. Why can we estimate these pi's by OLS? Is look at the reduced form equation on the screen. The reduced form equations have only exogenous regressors on the right hand side, the variable x1. So we can apply OLS without a problem. And if we apply OLS, we can estimate separately these two equations, y1 and y2. And we can have the values of pi 1 0, pi 1 1, pi 2 naught, and pi 2 1. These are the reduced form coefficients. In fact, these are two straight lines, regression lines, simple regression lines. And you can use the slope and intercept formula in Microsoft Excel, or you can use the regress command in Stata to estimate an equation y1 on x1 or y2 on x1 and get the values of the reduced form coefficients pi's with different subscripts. So using these estimates, we can, by using the information that we derived by substituting pi 1 1 and pi 2 1, etc. So you can easily see that if we divide pi 1 1 by pi 2 1, we are left with alpha 1. This is the indirect least square estimation of the structural parameter alpha 1 of first equation. If you perform an order condition, you will easily see that the first equation is exactly identified and the second equation is unidentified. So you can estimate the structural parameters of the first equation by expressing them in terms of some reduced form coefficients, and you can estimate those reduced form coefficients by ordinary least square. And so you are indirectly estimating alpha 1 and alpha naught by performing two OLS operations. So when you perform two OLS operations on first reduced form equation and the second reduced form equation, you can substitute pi 1 1 and pi 2 1 in the expression alpha 1 ILS is equal to pi 1 1 over pi 2 1. As you see on the screen at the end of the expressions, alpha 1 ILS is equal to pi 1 1 over pi 2 1. So this gives a value of alpha 1, which is called an ILS or indirect least square value. So this is the way we perform indirect least square. Now let's see whether these values are identical to two-stage least square values or no. For that we need to know what is pi 1 1 and pi 2 1, and we can substitute that. So look at the two reduced form equations that we had just shown. You are seeing them again. So if you remember the OLS or simple regression equation, y is equal to a plus bx, you remember we wrote them into reduced form. Small y is equal to b times small x, and this way we can estimate b as summation xy over summation x square. So remembering this information, that we can express b as summation xy over summation x square, where xy and x square are in fact x minus x bar, y minus y bar. Remember the deviation form? We substitute x minus x bar as small x and y minus y bar as small y. In that way we can express b, or the slope of a straight line or regression equation, as summation xy over summation x square. Remembering this expression or formula, you can easily see that pi 1 1 can be expressed as summation x1 y1, small letters, remember the deviation form, and pi 2 1 can be expressed as summation x1 y2 over summation x1 square from the second equation. So these two expressions provide the OLS estimates of pi 1 1 and pi 2 1. And if you divide pi 1 1 by pi 2 1 from the previous slide, you know that it is equal to the parameter alpha 1 by ILS. So let's divide that. When we divide that, summation x1 square will be cancelled out, and we will be left with an expression summation x1 y1 over summation x1 y2. So remember, the alpha 1 which we have theoretically estimated and written as an expression can be given as summation x1 y1 over summation x1 y2, and this summation x1 y1 and summation x1 y2 can be estimated if you have some kind of data, and you will have a value of alpha 1, which is the ILS or indirect least square value of the structural parameter alpha 1. Remember this expression. In some time we will be performing two-stage least square to find the same parameter alpha 1, and we'll see whether we get the same expression or no. Now what do we do in two-stage least square? As the name suggests, we have two stages. If you have an equation y1 on y2, as you have in the model we are considering, then y2 is an endogenous variable. In stage 1 we will estimate the reduced form of this y2 and find the theoretical trend values of y2. We will replace these trend values y2 hat or trend values of y2 in equation 1. Instead of y2 we will be using y2 hat, and we will perform another OLS regression in stage 2, that is y1 on y2 hat. Instead of regressing y1 on y2, we will regress y1 on y2 hat. You can do it in Microsoft Excel or Stata, whatever you like. Now look at this procedure theoretically. On the screen you are seeing that we estimate y2 hat and replace it in the first equation, because the reduced form of y2 is given as pi 2 naught plus pi 2 1 x1 plus u2. If we estimate the trend values, if we estimate this pi 2 1, you can use the slope formula in Microsoft Excel, or you can directly use the regress command in Stata and find the values of pi 2 1. So this is an estimated value of pi 2 1. So using this estimated value, if you find y2 hat, it would be expressed as pi 2 1 estimated times x1. So as you are seeing on the screen, y2 hat is given as pi 2 1 hat x1. Now we'll replace this y2 hat in the first equation to perform the second stage of the 2SLS regression. So y1 was alpha naught plus alpha 1 y2 plus e1. Now instead of y2 we have substituted y2 hat. So we have y1 is alpha naught plus alpha 1 y2 hat plus e1. So again remember the formula I just told you. Remember from the simple regression equation, you have an expression for the b, the slope coefficient, summation xy over summation x square. Now instead of x you have x1, or you may have y2 hat in place of x, and you may have y in place of y, so y1 in place of y. So using the same technique or expression, you can see that alpha 1, which is given as a two-stage least square alpha 1, can be written as summation y1 y2 hat over summation y2 hat square. Now remember that you know that y2 hat is pi 2 1 hat x1. Now we substitute this pi 2 1 hat x1, and we get the expression summation y1 pi 2 1 hat x1 over summation pi 2 1 hat x1 square, as you are seeing on the screen. Now this pi 2 1 hat is an estimated value, so we can factor it out. We can write it on the left side of the summation notation. So pi to 1 hat over pi to 1 hat square is into summation x1 y1 over summation x1 square. So after cancelling and performing some operations, you can easily see, as you are seeing some expressions on the screen, that some of the values will be cancelled out, and the end result of this operation is that you get the two-stage least square estimates of the structural parameter alpha 1 as summation x1 y1 over summation x1 y2, which is exactly the same as you did when you performed the indirect least square. So presently we have theoretically shown that if you perform ILS or two-stage least square on an exactly identified equation, you may get the same results theoretically. Now let's move to an example which will show you the numeric value of alpha 1 is the same for exactly identified equations, whether you apply ILS or two-stage least square. The example is given to you in the Excel file ILS-2SLS.XLSX. This file is provided to you. So looking at that data, you can yourself perform this task in Microsoft Excel or in Stata. So let's look at the example. So consider the model where you have two endogenous variables y1 and y2. You are viewing that on the screen. y2 exists on the right hand side of equation 1 as well. If you apply order condition, you can easily see that the first equation is exactly identified as we did before, and we have two reduced forms. So we have reduced form for each endogenous variable. So as we have two endogenous variables, we have two reduced form equations. Pi 1 naught plus pi 1 1 x1 plus u1 is equal to y1, and y2 is pi 2 naught plus pi 2 1 x1 plus u2. So remember I told you, you have a file ILS-2SLS.XLSX, which is an Excel file. You have the data in it. You can use Microsoft Excel, or you can paste it in Stata and use Stata. Now here in stage 1, as you know that pi 1 1 and pi 2 1 were names of some expressions. We labeled some expressions as pi 1 1 and pi 2 1. So we labeled alpha 1 beta 2 over 1 minus alpha 1 beta 1 as pi 1 1, and beta 2 over 1 minus alpha 1 beta 1 as pi 2 1. So using this, we can estimate pi 1 1 and pi 2 1. I have done that by using the slope function in Microsoft Excel. So if you write equals slope and the y values and the x values, you will get the parameter pi 1 1 and parameter pi 2 1. The difference is that in pi 1 1, to estimate pi 1 1 by the slope function, you regressed y1 on x1, and to estimate pi 2 1, you regressed y2 on x1. So these are the slopes, in fact, of these two reduced form equations. So using these, pi 1 1 over pi 2 1 gives a value 13.51659. This is an indirect least square value of the structural parameter alpha 1, which was a structural parameter of the original equation 1, which was an exactly identified equation. So this is an ILS value. Now let's see if we perform the 2SLS procedure, do we get the same 13.51 or we have a different value? So now you are looking at a column on the screen, y2 hat. For example, the first value is 0.669191. This is an estimated, this is a trend value of y2 hat when you regress y2 on x1 in this model. So this is your stage 1. In stage 1, we regress y2 on x1 and perform and calculate the values of y2 hat. These are the theoretical values. In stage 2, we will replace this y2 hat instead of y2, in place of y2, and perform a regression y1 on y2 hat. So you have this column as well in the file. So just perform a regression or use the slope function in Microsoft Excel, or use Stata as you like, and you will see that if you regress y1 on y2 hat, you get a value of slope coefficient of 13.51659, which is exactly identical to the value through indirect least square. So you saw theoretically that how the structural parameters through indirect least square and those through two-stage least square are theoretically exactly identical in case of exactly identified equation. And similarly, you also saw an example where the values, numeric values of this structural parameter, obviously if theoretically they are equal or identical, they would be equal or identical numerically. So that is 13.51, which is identical in both cases. So what we conclude is that if you have exactly identified equations, ILS and 2SLS would be providing identical results. Let's discuss another useful estimation method, which is called three-stage least square, which you can say is an extension to two-stage least square methodology. So remember that ordinary least square is inconsistent or provides inconsistent estimates of the parameters in case of simultaneous system of equations. So you shouldn't use OLS to separately estimate equations when the equations should be simultaneously estimated. And remember that two-stage least square, we clean the endogenous regressors. In stage 1, we estimate the reduced form of the endogenous variables and find their theoretical or trend values. And in stage 2, we replace them and find the first endogenous variable or the endogenous variable for the over-identified equation. And we regress it on the endogenous variables' theoretical values or trend values, and we get the 2SLS estimates of the structural parameters. So also remember that in two-stage least square, one endogenous variable may be related to the error term of the second or third or any other equation. So, but two-stage least square misses something. There is a problem here. First, we are only focusing on a single equation at a time. So when you perform 2SLS, you are focusing on the over-identified equation normally. Remember that you cannot apply ILS to over-identified equations. You have to do that through instrumental variable or two-stage least square. So when you apply 2SLS, you perform two stages. One thing you are not accounting for. That is the possible correlation between the residuals or disturbances or the error terms of several equations. What you accounted for was the possible correlation of one endogenous variable with the error terms of several equations. Now I am talking about the possible correlation of the residuals, for example, as you denote them E1, E2, E3, U1, U2, U3, etc. They also may be correlated. They may have a correlation structure, a significant high correlation. So in two-stage least square, we ignore that. So this is why three-stage least square methodology was devised by Zellner and other authors in 1962 in a famous paper in Econometrics, and they provided an estimation technique which includes a third stage. So the first stage, two stages are similar, and you have a third stage which shows how we can estimate 3SLS structural parameters. So you are seeing a statement, endogenous variables may be related to error terms of other equations. This was in two-stage least square. So if you remember the reduced form, when you substitute one equation in the second, then the first variable becomes a function of the error term of the second variable. In fact, the endogenous variable on the right-hand side of the first equation is related to the error term because it is a dependent variable in the second equation. So if you have the system of equations in your mind. So this was a problem in 2SLS. So what possible problem? Let me list the possible problems in two-stage least square so that you can decide when to use three-stage least square if possible. So as you see on the screen, the first problem stated is we focus on a single equation in the system. This is the over-identified equation that we are focusing on. Even if we have more than one over-identified equations, we focus at a time on one equation and estimate the structural parameters of that single equation. So this is the first issue. Second, as you see, we have correlations between error terms of various equations, which is ignored. So if you have two equations with disturbance terms E1 and E2, then E1 and E2 may be correlated, and 2SLS ignores that. So in this way, 2SLS may provide inefficient estimates. In that case, we have the three-stage least square to be used. So in a paper in 1962 in Econometrics, Zellner and Thiel provided the third stage, which accounts for the possible correlations between the error terms or disturbance terms of all the equations in a simultaneous equation model. So it takes into account the intertemporal correlations of E1, E2, E3 as you label them normally. So E1, E2, E3 are the error terms or residuals or disturbances, and the intertemporal correlation structure is considered in the three-stage least square methodology. So 3SLS uses the results of 2SLS. As I told you, the first two stages are identical. We add a third stage, and due to that third stage, we have estimates that take into account the intertemporal correlations of the disturbance terms of the system of equations. So 3SLS is more efficient as compared to 2SLS. So it provides it works better when the correlations between these error terms are high. So if the correlation between the error terms of different equations is very low, so maybe 2SLS provides better results. But when the correlation is high and higher, we get better and better and better results when we apply three-stage least square. So remember that if you have correlation structures such that the error terms in different equations of the simultaneous model are not well correlated, use 2SLS. And if they have a high correlation, prefer three-stage least square. You can normally look at the root mean square error, etc., and these things, and see which of the two estimates is better. So as we do in three-stage least square, we perform the first two stages in 2SLS, and we have a third stage. We estimate the correlation or covariance structure of the system of equations. There was a command in Stata reg3 that you had used for estimation of structural parameters by two-stage least square in Stata. And if you remember, we used an option after comma, 2SLS. So in fact, the command was for three-stage least square. We gave an option 2SLS to perform the first two stages only. So when we don't give this option of 2SLS, we will get three-stage least square estimations by default. Let's look at this command and take example of how to use it. So first look at the structure of the syntax of the command. As you see on the screen, in a box, reg3, then you have parentheses, dependent variable 1 and variable list 1. So you have one dependent variable and a list of explanatory variables which may include the endogenous variables of the system. Separated by parentheses, you have another set of equations that is dependent variable 2, variable list 2. This means you may have a second dependent variable and a second variable list. And you may continue to n equations. You may have n equations in a system of equations. So dependent variable n, variable list n. You have in square brackets if, in, and wait. So this if, in, and wait are three options that you can use in this command, because remember that when you have square brackets around something in the syntax, they are optional. You write them or don't write them. Now also remember that in Stata, we have two ways to perform a task. We can use the graphic user interface and we can use the command window. So if you want to know how to perform reg3 by using the graphic user interface, remember that we use the command help. So if you write help reg3, you will have the help window open and you will have a menu in that help window. That menu will tell you how to click and where to click and get a window to provide information and get the three-stage least square estimations. So you are seeing that menu on the screen. You will click on statistics, then on endogenous covariates, then on three-stage least square. So you will get the syntax of how to use the graphic user interface for three-stage least square. So let's open a file to take an example. I do that by using a command webuse. Remember that webuse will open a file from the web. It will download it and you will have the file in the memory. So when you use webuse, the file name is Klein, K-L-E-I-N, and if your internet is working, you can get the file in your right side window. Remember that there is a window on the right side called variable window. If you get the variable list, this means that file has been loaded into the memory. Now how to know about the file? Use the commands describe, summarize, list, etc. For example, if I type describe, I get the results that you are seeing on the screen. So the results are that the file contains data from a web address, that is Stata Corporation, Stata Press, and there is a long address with a file client.dta. Remember that DTA is the extension of a Stata file. You have 22 observations, 14 variables, so the size is 1232. So since you use the describe command, you have a description of what you have in this file. The first column is the variable names, year, consumption, profits, private wage bill, investment, capital, etc. Lagged value of capital stock, because theoretically we think that consumption or other variables are affected by, or investment is affected by the lagged value of capital stock. So it is taken here, capital 1 is the name of the variable. And similarly, you have government wage bill, you have total income by demand, and you have the tax values and other things as well. The last year's total income, and if you want to use lagged models. So this provides you an insight into what is available in the file. Similarly, you can use the list and summarize commands. Now let's specify a model. In the model you are seeing on the screen, you have two equations. In the first one, consumption is your endogenous variable, and it depends on private wage bill and government wage bill. In the second equation, you have private wage bill as an endogenous variable depending on consumption, government, and capital 1. So these are your two equations. So you have two endogenous variables, consumption and private wage bill. Now using the graphic user interface as you are seeing, the file was already open. So keeping these two equations in mind, I click on the statistics, on endogenous covariates, and then on three-stage least square. The window that you see on the screen will open. So see on the left side, you have several equations, equation 1, 2, 3, and so on. At a time, you will select one of them. For example, I clicked on equation 1. Then on the right side, you see that I had clicked on an arrow, so I have a list of all the variables in the file. So I can one by one select the variables. For example, dependent variable for equation 1 was consumption. So I'll click on consumption. And when I select the dependent variable for equation 1, then I'll press tab or move to the independent variable field, and now I can select more than one variable. So I have selected private wage bill and government wage bill. You can click one by one on the variables and they will be selected in this field. So this was for equation 1. Now you need for equation 2 or 3 or as many equations you have, you can specify them. So now you will click on equation 2, and after clicking on equation 2, you will select the dependent and independent variables in the same way as you did. And after that, look at estimation methods, by, if, in, weights. These are the ribbons provided in this window. You can specify them, but presently we don't do that. You also have something below the variable list, that is iterate. So we can use iterated three-stage least square as well. So presently we are not going into detail of that. We'll click OK and we'll get some results. So when you selected the variables for equation 1 and equation 2, you did not specify which are the exogenous or which are the endogenous variables. You did not use these options. You just have specified the two equations and ordered stata to perform a three-stage least square. This is the default operation. If you give another operation or option, for example, after comma you write 2SLS, then two-stage least square will be performed. If you don't give an option, then three-stage least square will be performed. So note that when you get the results, I would request you to perform 2SLS and 3SLS, and you will see for the data I have provided you that the root mean square error is less in case of 3SLS as compared to the two-stage least square estimations. That's an indication that 3SLS is a better approach here. So let's look at the results. So when you use the graphic user interface by clicking on stata, etc., statistics, etc., and perform the operation as I told you, you will get the results that you are seeing. So first of all, note the command on the top. If you would have written this command and entered, you would have got the same results. So reg3 is the command, and you see that in set of parentheses, we have the two equations. So consumption on private wage bill and government wage bill, and private wage bill on consumption, government, and capital 1. Remember, capital 1 is the lagged value of the capital stock. So this gives you the three-stage least square regression as you see on the screen. So the root mean square error for consumption and private wage bill are 1.77 and 2.37. I haven't shown here, but I performed 2SLS and the root mean square error for these two was much more. So the p-value indicates that this is significant. So the model is a good fit. So look at the two small tables given below. First one is for the first equation, second for the second equation. So consumption was regressed on private wage bill and government wage bill, and private wage bill was regressed on consumption and the variable government and the variable capital 1. You have intercepts. So remember here, if you specify an option no constant, you wouldn't have these intercepts. And below these tables, you have endogenous variables and exogenous variables. This was automatically set by stata. So as you wanted, the endogenous variables are consumption and the private wage bill, and the exogenous variables are government wage bill the variable government and the variable capital 1, which is the lagged stock of capital. So all the other variables with the exception of consumption and private wage bill are exogenous. Now look at the slope coefficients, the first main column with numeric values. For example, in front of wage private you have 0.8 and then government wage bill 1.02. You will interpret them in the same way as you did with normal regression equations. Look at the p-value, 0.0 for the private wage bill, 0.001 for the government wage bill. All are significant. In the second equation, the variable government is only significant and the variable consumption is just significant at 11.7%, slightly above 10%. So you don't get significance here. So the number one, the correlation of endogenous variables with the error terms of the other equations and the intertemporal correlations of the error terms of a system of equation. So the main thing in three-stage least square was that you have taken into account the intertemporal correlations of the error terms, or you can say the correlation structure of the error terms in a system of equations that may be over-identified or even exactly identified. So you can specify the other options as well. We will speak about the options in some time, but remember that three-stage least square has an edge on two-stage least square, that it has taken into account the correlation structure of the disturbances or residuals. So when you use two-stage least square or three-stage least square, you can look into root mean square error as I suggested to you and see that you will see or try to observe. If you try to observe, you will know that as you have higher and higher correlations among the error terms of the system of equations, three-stage least square is better, and when you have low correlation, sometimes 2SLS provides better estimates. So besides this estimation and this example, now we can speak of different options that are available with this command reg3 or reg3. Remember that options in stata commands are given after a comma. So you have the basic command syntax, and after a comma, you may have different options. How to know about these options? Just type help and reg3. The help dialog window will provide you with different options. I'll show the options to you on the screen in some time. Remember that some of the options can be simultaneously used and some cannot be simultaneously used. I'll not discuss all the options. I'll discuss few of the options. If you move to the help window, you may look at the description of all the options that you can use with the reg3 command. So let's look at the options of the reg3 command available in stata, some of them. So as you see, the first option is no const. So it omits the constant term for an equation if specified an equation. So as you saw on the screen, you had an option no const written after comma. So you can specify the no const option for an equation. So in that case, it will omit the constant term for a single equation. You may omit the constant term for the instrument list, that is stage 1 of the three-stage least square procedure, if specified overall. So if you overall specify the no constant option, the no const option will not be used, the intercept term will not be given in the first stage of the 3SLS in this stata operation. The second option is ireg3. This is an iteration. So as you see, the iteration over the estimated disturbance, covariance matrix and parameter estimates until the parameter estimates converge. So until the convergence is established, the iteration will continue, and after convergence, you will have the results in front of you. After several iterations, you may have 3, 2, 5, 9, any number of iterations. And if it converges, you will get the results on the screen, which are the two-stage iterated three-stage least square results. So the options no const and ireg3 can be used simultaneously. Look at the other options. You have the option SURE, which is seemingly unrelated regressions. This is another regression technique. So as you see, this performs a seemingly unrelated regression estimation of a system, even if dependent variables from some equations appear as regressors in the other equations. So also you have an option of 2SLS. So when you have this option, we have already used that. So if after comma you just try 2SLS, then only two stages will be performed and you will have the results of the two-stage least square. So when you want to apply two-stage least square methodology, just give an option, comma, 2SLS, and you will get the two-stage least square options. Another option is first. So if you specify first, you are actually requesting a display of the first stage regression, the regression results in the first step, which we have performed in 2SLS as well and in three-stage least square. So you can use these options with 2SLS also. So you can use 2SLS and first at the same time. Similarly, you have an option CORR with, as you are seeing on the screen, correlations in parentheses. So this specifies the assumed form of the correlation structure of the equation disturbances. That is the correlation between error term 1, error term 2, error term 3. Remember that this is rarely used, and I don't think that you will ever need or you will ever use it, but it's an important option. If sometime you have assumed a correlation structure, then specify that correlation structure by the core and correlations in between the parentheses command. So another one is small. So if you use the option small, then you will get the small sample statistics along with the regression results. So do that only if you have a small sample. And obviously there is another option, 3SLS. This is the default option. So if you write after comma 3SLS, you will be getting 3-stage least square results. And if you don't write this option, this will be performed because this is a default option. So if you don't write it, you will get 3-stage least square results. So today you learnt how to perform 2-stage least square and 3-stage least square. You also learnt that 2-stage least square and 3-stage least square will be providing identical estimates if the equation is exactly identified. So remember that OLS is applied to a single equation. If you don't have a system of equations, you can do that. If in fact you have exogenous variables on the right hand side and one endogenous variable on the left hand side. So when you applied 2-stage least square or ILS, it was the case when you had a system of equations. So whenever you have a system of equations and you want to estimate the parameters of those equations, which we call structural parameters, you will try to choose a technique. To choose a technique, you can apply order condition or solve the model to get the identification status of the model. If you feel that the equation is exactly identified, you have a choice of using indirect least square or 2-stage least square. Theoretically, you should use ILS. But as you know, and we have demonstrated, that 2SLS and ILS provide the same result for exactly identified equations. So you can safely use 2-stage least square, or as later on we did, 3-stage least square. So if one or more equations are over-identified, you cannot use ILS. You can use both techniques only if the equations are exactly identified. If you have over-identified equations, then you have a choice between 2-stage least square and 3-stage least square. Now, normally how to choose between them is that you look at the correlation structure of the disturbance terms. You assume that. So you think about it because you don't have the correlation structure beforehand. So you will think about it. If you feel that the error terms are correlated, so the intertemporal correlations between the disturbance terms of the system of the equations in the system is high in your opinion, then prefer 3-stage least square. And if it is not, use 2-stage least square. It may be more efficient. So you can do both. You can use 2-stage least square and then 3-stage least square and compare the results, look at the root mean square error, etc., and decide for yourself. You can have the correlation structure in front of you. So basically the difference between 2-stage least square and 3-stage least square is that in 2-stage least square, in the 2 stages that we performed, we didn't take care of the intertemporal correlations of the disturbance terms. But in 3-stage least square, we took care of the intertemporal correlations of the disturbance terms. In the 3rd stage, we estimated that correlation and covariance matrix. So this is how we use either of OLS, ILS, 2-stage least square or 3-stage least square. Remember, for all these models, you have either cross-sectional data or time series data. The next lectures will combine the cross-section and time series and look into panel data methodologies. But presently, we use either single equation or multiple equations by using either cross-sectional data or time series data. In these cases also, you should perform some tests, for example, as we did today, the test of endogeneity, whether the regressors were really endogenous or no. So after you are satisfied, you can report your results. Thank you very much for today.